Hey troopers, great to have you all here and great being part of this beautiful event. So, as you've realized, this is a little bit of a different talk that compared to the original agenda. We have got an upgrade to track 1 and we will give our best. And at the end, we have stickers for you. So, what is today's topic? We will talk about firmware analysis, especially firmware analysis with EMBA. EMBA stands for Embedded Analyzer, and it is a fully automated security and vulnerability analyzer for firmware of embedded devices, for sure. And the best thing on EMBA is, it is open source. So, after our talk, you can go straight to our GitHub repo, download EMBA, start analyzing firmware, finding bugs and vulnerabilities, and at the end, making the Internet of Things a little bit more secure. So, my name is Michael Messner. I am a penetration tester at Siemens Energy. And during my daily business, I perform penetration tests on critical systems and environments. And this is the area where we started developing EMBA, and where we are using EMBA on a regular basis. And yeah, with this in mind, I will hand over to Pascal, who will give you a great overview on firmware analysis and EMBA.
Thank you, Mike. My name is Pascal Eckmann. I am a cybersecurity engineer at Siemens in Munich, and I also have some experience in security research, especially in the field of firmwares and embedded devices. Now, as you all know, we have way too many IoT now in our lives, so it's everywhere. Starting from your smartphone over to the smartwatch on your wrist, to the car which you are driving to work, over the centrally controlled traffic lights, and the factories with their huge array of machine controlling devices and other critical infrastructure. With this huge amount of IoT devices, we have to think about security. We have to make those devices more secure. And there are many ways to do that. And we now just focusing on the firmware part of the IoT world. So what is firmware? Firmware is the operating system of these so-called embedded devices. It can be a huge Linux system like Ubuntu, or something small, quite exotic. There are many known Linux analysis techniques out there, many tools, but who knows them all? No one. And there are also some commercial tools, but they are quite expensive and their output is limited. And EMBA has no limit, costs no money because it's open source and gives you the best results overall. How? To answer that question, we have to walk through the typical manual workflow of a firmware analysis. We now assume we have a firmware at our hands, and then starting with the command strings. With the command strings, I can find some plain text. If I'm lucky, I can even find some passwords, like in this example. And then I execute binwalk. Then I have a file system of my firmware. And in this file system, I can now execute find, looking, for example, for configuration files, and then can use grep and regex to find some some information in those configuration files. In the meantime, I will Google a lot, trust me, a lot. And after maybe some hours, I will dump something from the firmware into a decompiler like IDA or Gitwa. And if we are summarizing this workflow, then we can say it's a mess. You will try everything, you will focusing on the difficult parts of the firmware, and you will waste a lot of time. And that's a problem. No one has time. And that's the point where EMBA will help you. As Mike already told us in the beginning, EMBA is short for Embedded Analyzer, and it's an open source tool which helps you or takes away from you the manual labor which is involved in a firmware analysis. With EMBA now, the process to analyze a firmware is really easy. You just have to get the firmware, then start EMBA with just one command, and then EMBA will take the work from you. So EMBA will now extract the firmware, then analyze it, and at the end you will get a nice report with all the interesting parts of the firmware. So there is one manual step involved at the beginning. We have still to get the firmware. And how to do that? So there are some ways to get your hands on a firmware. And the easiest one would be to visit the web page of the vendor and then download the firmware from there. That's often the case if the device is not being updated over the air. If you are lucky, you maybe already have shell access to your device and then can copy the file system from the device to your storage device via a known protocol. Or you are capable of exploiting an already known vulnerability on maybe a command injection on the web interface of your router. If those methods didn't work for you, you now can focus on the hardware itself. There are some ways to get the firmware even from the hardware. One way would be to access the device over a debugging interface like JTAG or SWD. Another way would be to sniff the communication from the flash to the memory while the device is booting. In the boot process, a device needs to copy the complete firmware from the flash to the memory, and that's the point where you can get the data. And another way would be to desolder the flash memory from your PCB and then extract the content from it. So let's now assume we have a firmware. And we now start EMBA with the firmware, and EMBA will now start its extraction process. And the easiest way overall to extract a firmware binary would be to use binvoc. If the firmware is quite basic or nothing special, then you will get a file system afterwards. But we have a little problem. binvoc is since a while no longer under active development, and therefore we started to invest some time into the extraction process of EMBA. Let's walk together through the extraction process. EMBA has some extraction modules, and for example, the first one is for the basic compression, like a zip or something like that. And EMBA will now extract it with part tools. Or if we have a external or a UFS file system, then we will mount it and then copy it to your file system. Or the same happens if it's a VMware image. If it's a encrypted image and the key is already been leaked on the internet, then we have the key, then we will implement it into EMBA, so EMBA is now able to extract also those firmwares. Then there are some special images like from the vendor, like AVM, a German manufacturer for routers or other home network stuff. And there are some custom tools like FreezeNG, which is capable of extracting firmwares from AVM. And at the end, if there are some other systems left, then we will use binvoc. And now EMBA will check for a Linux root file system. If it finds one, then it's nice. EMBA can start the analyzing modules, and we are in the next step. But what would happen if EMBA does not find a Linux root file system? Then EMBA will start its special feature. It's a deep extraction mode, and the deep extractor of EMBA re-extract already extracted file systems. So if there are some packages like deb archives or something like what Binwalk could extract inside of your already extracted firmware, it will be now extracted, and then EMBA will rerun the deep extraction as long as possible. And in the end, we have a really good extraction of the firmware, and our results were way better than before. And after that, we try, or EMBA tries, to find a Linux root file system. And even if there is no Linux root file system, now EMBA will also start the analyzing modules, because EMBA is quite capable of analyzing a firmware even if it's not a Linux-based system. So now we have a file system, and we have many questions about the firmware. We want to know many things, and for example, which files are in this firmware, which architecture is this complete firmware based on, or which software versions, or which areas are from the vendor, or which is basic Linux files. And all those questions and even more will EMBA now give you, so that you will get an answer from EMBA. And how does EMBA do exactly that? And why is EMBA so good doing exactly this? We don't want to reinvent the wheel. There are many amazing tools from our community, like from you guys, which are quite useful in analyzing Linux firmwares, also in Linux-based firmwares. And so we are using those tools inside of EMBA. So you just have to run the installer, and with the installer, all those tools will be installed on your system inside a Docker container, so the installer will download it. And then you just have to use one command, and you will get a full firmware analysis. And with that, now we want to find out more about finding vulnerabilities with EMBA. And now I will hand over the stage to Mike.
Pascal. Thank you for a great overview. So now we have to talk about two more topics. On the one hand, about the identification of zero-day vulnerabilities, and on the other hand, on one-day vulnerability identification. As you probably think about, zero-day identification is quite hard for an automated analyzer. So EMBA will point you into the right direction, so that you as a penetration tester know which area of the firmware you should spend more time. So, but first things first. What is a zero-day vulnerability at all? I think most of you are aware of it. So a zero-day vulnerability is a currently unknown vulnerability. This means that there are no patches or security updates available, or other remediation mechanisms. From a penetration tester perspective, a zero-day vulnerability is quite interesting because we have to find it by ourselves. No vulnerability scanner will find it. You need your own scripts, your own fuzzer. If we talk about web-based stuff, then we need a proxy. We need to analyze the communication and so on. And at the end, we need our own creativity, our own brain. And this is more or less the goal of every penetration test. No, the goal is to spend as much time as possible in identification of zero-day vulnerabilities. And all the other stuff that can automate it should be automatically happen. And this is the area where EMBA comes in place. So regarding the identification of the juicy stuff within a firmware, we have implemented different metrics within EMBA. So one of these metrics is legacy C functions. You will find a lot of legacy C functions within firmware. And by definition, a legacy C function by itself is not a security vulnerability. It's probably, let's say, something like a violation against the secure software development lifecycle. But if such legacy C functions are used quite massive, then the possibility that something goes wrong is quite high. So at the end, we need something like a counter. How often such a legacy C function, like a string copy, is used in every binary and every library. So as a first indicator, you can probably use readelf. Just write a short shell script, use readelf on every binary and library, and then you get the information, string copy or this legacy C function that you're interested is used in this and that binary. But you do not know how many times. So under the hood, EMBA is using object dump and Radari 2. Object dump in first place because it's quite fast and very reliable. But sometimes object dump will fail, and then EMBA automatically brings Radari 2 in place. At the end, EMBA generates a full disassembly of every binary and library within the firmware. And now we are able to do some further analysis. We can, for example, just count the functions that we are interested. So we can just count string copies. But as we already have the full disassembly of every binary and library, we can do further stuff. We can, for example, check if in the last, for example, 20 instructions, right before the string copy is already a string length in place. So then it's probably from an analyzer perspective, we will take a look at another string copy before. But there are lots of other things that we can now do. For example, we can answer the question if this binary has network functionality included. We can just check some network functions, and we know, okay, the binary has now or is using string copy massively and has network functionality included. That could be interesting. But I'm sure a lot of guys from you know the handy tool checksec.sh. We can also automatically now check the binaries and libraries against binary protection mechanisms. And finally, EMBA includes a list of well-known Linux files, just the names. And yeah, this approach is not bulletproof at all, but let's say it is something like an educated guess that EMBA can do. So now we have an educated guess that this binary that has a lot of string copies is not a Linux binary. What else it is? Probably it is a binary from the vendor. And then we will take a deeper look at it. So at the end, EMBA will help you in identification and taking a look at the interesting spots within a firmware. This is the final report. It is a web-based report that EMBA spits out. And I like challenging EMBA from time to time with public advisories. For example, this is based on a firmware that a guy, a security researcher named Stereotype32, he has released a bunch of vulnerabilities in such a Netgear router or Netgear device. And I've tested EMBA if EMBA will point me to the right direction. And you can see some interesting details here. For example, you can see that we were able to identify the string copy use 3,000 times. And 1,500 times, string copy was used in a binary called setup CGI. And the setup CGI is rated as a non-Linux binary, probably a binary from a vendor. Then there are no binary protections available. And yeah, it's not no network capabilities were detected, but that's not the big issue because it is a CGI, so the web server is the process that gives the binary the network capabilities. Additionally, EMBA has found that this setup CGI binary also uses, I think, 200 times the call to system. So from a penetration tester perspective, I will take a first look at this binary. And while I now know where to look manually, EMBA will help me in the background in the identification of all the known vulnerabilities, the so-called one-day vulnerabilities. So, what is a one-day vulnerability? It is an already known vulnerability. This means, in theory, there are already patches and remediations available. From a penetration tester perspective, such a one-day vulnerability is completely different, because you do not need to identify the vulnerability by itself. You need to identify the software component with the exact version information. So at the end, this means you need to generate or create something that is called a software bill of material. And with this software bill of material, you can query further databases like a vulnerability database. Then you have, let's say, the vulnerability bill of material. And with this vulnerability bill of material, you can query exploit databases. And you get the exploit bill of material. Quite nice and shiny. And for me as a penetration tester, this should appear automatically. I don't want to waste my time in which bash version is there in place, which BusyBox version is in place, which web server version is in place, and I don't want to query all of the databases manually. So this should completely work completely automated. Sorry. But what is the problem with this process? Yeah, first of all, we are working on a binary blob. We are working on a compiled or packed firmware. Pascal has already mentioned that our extractor modules are doing a quite good job. So we get, in an ideal world, we get a file system out of this binary blob. So, one important thing, we do not have a source code available. So we can't go to a software repository, just query the software components, including the version details. Yeah, I know there are GPL packages sometimes, but they are very often so messy that it's easier to work on a binary level. And it's a completely different approach. So there is no standardized format of such version identifiers. And also there is no standardized mechanism or parameter on how to query these version details. So you can see it over there, for example. If you query the version information from bash, you do it with -- version. And then you get something like a GNU bash, version something as a version identifier. If you're querying OpenSSL for the version, you're doing it with OpenSSL version, no minus, no minus, minus. And then you get something like OpenSSL number, and letter. And Perl, I love the Perl version identifier. -V, and then you get summary of my Perl revision 5 version, and so on and so on. So this means you need for every software component you want to identify, you need something like in regular expression, a predefined identifier for this version. And EMBA includes a lot of identifiers already. But to use these identifiers, you can use different approaches. We call it hybrid version detection within EMBA, because we do not just use static analysis, for example, via the strings command. You can just print all the strings and hope that there's somewhere the version identifier included, match it against the version database, and then you're good to go. You can also query the kernel version from the kernel modules, for example, with modinfo. Or some versions are hidden in the path details. But on the other hand, you can also just execute these binaries via dynamic analysis. So EMBA is creating a quite nice and shiny environment for the binaries, and it is executing these binaries with different parameters like -v, -- version, -h, -- help, and so on and so on. And this works quite good. And at the end, we're using both sources of information and match it against the database of version identifiers or the collection of version identifiers. And we get something like a collection of all of the identified software components of the identified versions out of the firmware. For example, you can see some examples: BusyBox, IP tables, EasyCast, multi-hub, DNS mask, and so on and so on. And all of these version identifiers are looking a little bit different. So this means if I query something like the CVE database with this mess of version identifiers, I won't get reliable results. So I need to normalize these version identifiers to a format that I can use for further processing. So you can see there is the output from a typical firmware. You have some results from static analysis, some results from dynamic analysis, and at least the kernel with the kernel version that is used from the firmware. And now we are able to query our first database. The first one that we probably want to take a look is the CVE database. We already have the software component, the version, and with querying now the CVE database via CVE search, we get all of the CVEs. So all of the known or publicly known vulnerabilities. And with these CVE identifiers, we are now able to query further databases, like the exploit database. Or there is an exploitation framework that is called Metasploit. We can check the Metasploit framework if there are exploits available for this vulnerability. EMBA has some further sources included, like Routersploit, like Linux Exploit Suggester. And additionally, we have also a huge database included, or data pool included, that collects proof of concept code and write-ups on GitHub. So you directly know where to look further for the next step. Also included the, I think, CISA database of the well-known or known exploited vulnerabilities. So from a security team perspective, if your firmware spits out something like this, then you know that you have a big problem. Most of the exploits also have some further metadata included, like is it a remote exploit, a local exploit, denial of service, or something else. So we can fresh our whole results a little bit up. And finally, as we have mentioned before, EMBA is generating an aggregated HTML report with all of the details included. So we now know details about the identified software components, which version we have identified. So the whole software bill of material we now know. We also have an overview of how many CVEs we have found, how many exploits in every component. In the report, we can just click on everything there, and we can perform a full drill down. Also some aggregated information like how many high CVEs we have identified, including how many exploits, how many Metasploit modules. This is an interesting information for the penetration tester because these are typically the first exploits that you probably want to test. And also how many remote exploits were we able to identify. And everything within a nice and shiny HTML report, you can do a full drill down within your browser, also regarding the weak or the legacy C functions. And yeah, that's it more or less. So EMBA, Firmware Security Analyzer. If you like it, go to our GitHub repository, download it, use it, give us feedback, what's not working, what you expect that should work better. And if you're a seasoned penetration tester, then I'm sure you have a massive amount of ideas. Open issues, open requests, contact us. We are happy if you're using it and you give it feedback. And so now, that's it. Thank you very much. And I think, do we have a few minutes for questions?
Yeah, thank you. Are there questions? Maybe, yeah.
So during all of the slide deck, if I would do this, was there any human interaction needed, or would EMBA have done all of this automatically after I somehow extracted the firmware and have that as a binary?
So EMBA supports a massive amount of parameters, but where you can optimize your firmware analysis process massively. But we have created some profiles that are, from our perspective, quite useful. And you can just scan or start a scan with I think 3 parameters: the directory where you want to log all the results, the firmware binary by itself, and finally the profile. And we have a default profile that I typically use also on my own tests. So the best way is to start with this and check out the help. Then you can see what other options are possible.
Further questions?
Thank you very much. I know the intent of this project was to analyze firmware in particular, but if, for example, I had a tarball of a file system layer from a container, for example, could I also use EMBA to analyze that for a bill of materials, software vulnerability bill of materials, and so on?
Two things. We support container analysis directly. If the container is running or on your host, you can start EMBA with the container ID, and then it downloads the container for you, extracts it, and it's automatically analyzing it. And if you have something like a tarball from a file system that you got from somewhere, from a dev team, or you extracted it somehow, you have 2 possibilities. First of all, EMBA can extract it for you, or you just extract it by yourself and you point EMBA to the directory where the file system is now sitting.
Hello, thank you for the talk. What is the difference between EMBA and the FACT?
Between EMBA and FACT? Currently, I don't know the recent version of FACT. The last time I've tested FACT is a few years ago, so I'm sure they made a lot of progress. So probably we need to evaluate it in detail. I don't know it currently, but as far as I know, FACT is more web-based. So you can upload your firmware to a web application, and then he's doing all his magic. And EMBA, in this version, is only a command line tool. We have also a web-based interface, but this is in a very early alpha state. But you can also find it on our GitHub repo. And from the results perspective, I don't know. So check it out and give us feedback if FACT is performing somewhere better than us, then we need to do something.
Further questions? Maybe I have one. I've seen you are doing your analysis basically for the user space programs. Do you also do some analysis for kernel modules?
We're doing some basic analysis. Yeah, we check the kernel modules, for example, on at least something like legacy C functions, like protection mechanisms. We also check the license of the kernel modules. So if there is a license called proprietary or not some open source license detected, then we will spit out a warning, because this is probably a vendor-based kernel module, and we should take a deeper look at this. Yeah, that's it. Bye.
Yeah. Okay, thanks. Further questions? If not, then we thank the speakers again.
There's another question.
Oh,
Thank you.
still a question.
In the meantime, we have stickers regarding EMBA. There's also the URL. So just take a few. We don't want to take it to home.
Yeah, one question I just had was, is there any support for mobile operating system analysis?
So from our perspective, we do not do mobile penetration testing a lot. But if you do it, please check it out. And if we are missing something, or you know something that we should support, you can include it in EMBA or talk to us, and we will find a way to bring it to EMBA. But I'm not a mobile penetration tester, and let's say it so.
Okay, I think now let's thank the speakers again.
Thank you very much.